My name is Jake Fulton, and I will be going over the needs of optimal and robust control for quad-rotor area vehicles, as well as control methods. In my research paper, I will be further investigating the results from the design and use of those methods. First step in creating a controller for a system is to understand why it is needed. This is an important step in deciding which control best fits the system. For a quad-rotor vehicle, there are challenges both externally and internally to the system. Some of the external challenges include atmospheric conditions and wind. The size of the quad-rotor vehicles can range from small drones for hobby use to larger vehicles designed for carrying items or recording images. In either case, winds can carry a lot of force, especially at higher altitudes, which could create a lot of instability for the system. Internally, the electronics of a control system would most often require batteries utilizing PWM to drive the motors, as well as several sensors to communicate the position and angle of the quadrotor. The graph on the right depicts data from a hobbyist's drone, which reports the pitch angle from the gyroscope after turning motors on. Even with no movement, there is clearly a lot of disturbance which needs to be filtered out. Additionally, the vehicles may often need to be used for several hours at a time, which means it will be important to maintain battery life. Before diving right into control methods, I want to mention some of the dynamics of a quadrotor. 4 different motors can be used in 4 different combinations to create the 4 essential movements of the vehicle, which are vertical movement, pitch, roll, and yaw. With these 4 movements, the quadrotor can move in any direction. However, a control system would be necessary to do that with any kind of stability. A PID controller would be a basic step up, with a transfer function for each input to each output. However, there isn't much to be done about noise and overshoots, which can lead to instability with some disturbances. Similarly, standalone LQR feedback likely won't be able to tune out the input and measurement noise enough to create a robust system, but it is a step up as it will be simpler to optimize specific state variables or inputs. For instance, greater weight could be put on the inputs in the cost function to ensure a longer lasting battery for use. To improve upon the LQR would be to add a Kalman filter. This would allow for optimization of specific inputs as well as reduce the noise and create a robust and optimized system. Alternatively, there is an option to use an H-infinity controller. While difficult to set up, it could produce an even more robust controller with strong ability to tune out disturbances and maintain tracking. The best way to consider which controller is best fit for the quadrotor would be to see experimental data, which will be covered in my research paper. These are the references used for the images above. Thank you.